What's up, mathematicians? Justin here, and in today's lesson we'll be looking at the constructions of the different triangle centers. In this video I'll show you how to construct and prove the circumcenter of a triangle. So here you can see I have a triangle, and in order to construct the circumcenter of this triangle I need to construct the perpendicular bisectors on all three sides. So I will start with this side right here. I'm going to go ahead and set my compass to be the length of the side, and go ahead and draw my arc there. Now I'll go to the other point, draw my arc again, and you can see those two intersection points. I'll go ahead and connect those using my straight edge. So I'll line up my straight edge like so. Let me get it as accurate as possible. I want this to come out nice and pretty. So, So there is the first perpendicular bisector. Now I'll go ahead and do this side right here. I'll set my compass to be that length. And I'll draw my first arc here. I'll draw my other arc. And looks like this one's a bit too big to fit on the screen here, but you can see that there's an intersection point down here and another one up here. In fact, my straight edge is barely long enough to connect them. So I'll line up my straight edge to be on those two intersection points. And once I have it lined up, I'll go ahead and draw in this perpendicular bisector. There it is. And now I just have one more to do, which is on this side right here. So I'll set the compass to be this length here. Keep it in place. All right. So there. And then the other arc right here. Okay. So now I'm going to set the straight edge to hit those two intersection points. Adjust a little bit. Okay, there we go. And there is my third perpendicular bisector. So we can see that the three meet right here at this common point. And that point right there is called the circumcenter. Let's write it right down here. So the circumcenter of the triangle is that point right there, where all three perpendicular bisectors meet. Now, since these are perpendicular bisectors, we know that this is a right angle, we know that this is a right angle, and we know that this is a right angle. Furthermore, I know that this length equals this length equals this length, and this length here equals this length right here. And one more thing I want to do with my circumcenter construction before moving on to the proof is show you that it is in fact the center of the circumcircle, which is the circle that will circumscribe the triangle. And this will also give me an idea of how accurate my construction was. So I'm going to set the compass to be the length from the circumcenter to any of the three vertices of the triangle. Then from there, I'm going to go ahead and make a circle. And if the circle touches all three vertex points perfectly, then I'll know that I've done my construction accurately. I'm running through my writing, but oh well. All right, so I'm going to draw my circle right there. And it's pretty good. It's pretty good. Let me darken it a little bit there. So that circle there is called the circumcircle. It's the circle that perfectly inscribes the triangle. In other words, it's the circle that touches all three vertices of the triangle. Now I did a pretty good job. It looks like it touches these two, but maybe just missed that one. There might be just a little bit of daylight there, but not too bad. So that's the circumcenter construction. Now we're going to move on to the proof of the circumcenter. Okay, so let's look at the proof of the circumcenter construction. And the given for this proof will be that I'm given a triangle, I'm going to call that triangle ABC, with perpendicular bisectors on all three sides. My goal is to prove that all three perpendicular bisectors meet at a common point. I'm going to prove that all three meet at a common point. Okay, so I'm going to take a bit of a different approach to this proof. I'm going to show you an example of a proof by contradiction. And we haven't done a proof by contradiction so far in this unit, and the logic of it is a little bit different, so it might be a little bit confusing. But the basic idea is this. If we want to prove that something is true, we can assume the negation of that thing. And if the negation of that thing leads to a contradiction, we can conclude that that thing is true. So, we're gonna, instead of just directly trying to prove that the three perpendicular bisectors meet at a common point, we're gonna assume that they don't all meet at a common point. And that will lead to a contradiction. This is based on the rule of contradictions, which is something that we talk a bit about in unit number 2. So our first step is actually to say the following. So step 1, assume that the three perpendicular bisectors do not meet at a common point. But instead meet at different points. But meet at different points. Now, mathematicians refer to this type of hypothesis, this type of statement at the beginning of a proof, as an RAA hypothesis. Now, you don't really need to worry too much about this, like the terminology side, but I will go ahead and explain it. RAA stands for reductio ad absurdum, which is Latin for something that we want to show is absurd or ridiculous. We want to reduce it to a contradiction. So we assume that the three perpendicular bisectors do not all meet at a common point. If we can use logic to result in a contradiction from that assumption, then we can come back to this and say it's false. If this is false, that means the three perpendicular bisectors do meet at a common point. Now, let's go ahead and put this in our diagram as well. So I'm going to draw, I'm not going to construct these. We already looked at how the construction would happen, but I'm going to go ahead and just draw sort of an eyeball approximation, although it won't be perfect because I'm purposely going to make them not meet at the same point. Okay, so this is going to obviously be an imperfect drawing for the purposes of the showing the contradiction. So I'm just going to pick two of these points, these non-common points. This point up here, I'll call this point J, and I'll call this point down here point K. So step one was the assumption. All right, so step two is going to be to draw the lines connecting J to the other three, to the three vertices of the triangle. So draw the lines JA, JB, and JC. I could have written CJ. It doesn't matter. It's the same line that I'm talking about. And of course, this is rule number 2 from going back to our axiomatic system that we have. Rule number 2 says I can connect 2 points with a line. Let's go ahead and draw in those lines on the diagram as well. We're going to be marking up this diagram quite a bit here. So I'm drawing these 3 lines. Like that. Okay. So now step number 3. Step number 3 is going to rely on the fact that these are perpendicular bisectors. So let's mark up the diagram a bit. Since these are perpendicular bisectors, we know that this is a right angle, as is this. These are right angles here, and these are right angles here. We're going to want to go ahead and label these 3 points as well. So let's see. Let's label them D, E, and F. Moreover, this distance here is equal to this distance here because this is a bisector. So the next step is it's kind of a compound step, actually. I'm going to state several different things. So I'm going to state, first of all, that BE, or I'll state it this way, EB is equal to EC. Those two are equal to each other. Also, these two angles are equal to each other. So JEC, angle JEC is equal to angle JEB. And then we have this side, JE, right here, which is shared by both triangles JEB and JEC. So JE is equal to itself because it is itself, and so these statements are based on the fact that we have a perpendicular bisector, right? So these angles are equal because of the perpendicular. These segments are equal because this is a bisector. Okay, well then we can say, step 4, that the triangle JEB is equal to the triangle JEC and since those two triangles are equal, the length JB is equal to the length JC. Now our justification there is side angle side, because this side is equal to this side, this angle is equal to this angle, and this side is equal to this side. Therefore, this triangle JEB is equal to the triangle JEC. Because the two triangles are equal, then these two sides are equal. So side angle side gives us that. Okay, well, now I can do the same thing with this perpendicular bisector and triangle JDA and triangle JDB. So let's go ahead and set that up. So step 5, I'm going to go ahead and point out that this length here is equal to this length here. And once again, these are both right angles. So DA is equal to DB. Then angle JDA is equal to angle JDB. And finally, JD is equal to itself. Once again, this is because of the fact that this line is a perpendicular bisector. Since it's a perpendicular bisector, these are both right angles. And since it's a perpendicular bisector, this length is equal to that length. Okay, so now step 6, we can say, well, wait a second, then this length JA is equal to JB. So JA is equal to, whoops, let me actually, I gotta specify the triangles first, I think. So let's write the triangles first. So triangle JDA. Oops, you can't even see what I'm writing, can you? So I want to refer to the diagram too, but I'll shift it down. So triangle JDA, triangle JDA is equal to triangle JDB. And therefore, JA is equal to JB. As we see here, JA is equal to JB, and that is also by the side angle side assumption that we have in our foundation here. So remember, other assumptions, side, 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 and side angle side, we haven't proven them. Maybe we will prove them later, but for now, we're just going to go ahead and put them as assumptions. So yeah, okay, so let's see. If JA equals JB and JB equals JC, well then all three of them must be equal. So step 7, JA equals JB equals JC. So because they're all equal, I'm going to make a little bit of a jump here, but stay with me. Because these three are all equal, then J is equidistant from the points A, B, and C. So, and J is equidistant. That means the same distance from the points A, B, and C. And so J is the center of a circle. Oops. Center of a circle which includes A, B, and C. Okay, so let's make sure we unpack that. What I'm claiming here is that since these three lengths are the same, then I could draw a circle, and you remember from the construction I did exactly that, right? I drew a circle centered at the circumcenter that included the three vertices of the triangle. Okay, so our justification here, well, these three are equal. That's the transitive property of algebra, and we've decided to put arithmetic and algebra in our foundation. So I'm just going to go ahead and state here transitivity. And I know I'm kind of pushing two steps in one here by doing the transitivity step and the equidistant step, the circle step, but I don't want to run out of space on my paper, so that's what I'm doing. So transitivity and the definition of a circle. You are, of course, welcome to separate the two steps. Okay, now I'm going to sort of make a little bit of a jump here to skip some steps, which might seem like cheating, but it isn't. Basically, what I'm going to say is this. I went through these steps to show that J is equidistant from points A, B, and C. I could just as easily have used the point K, though, because K is also the intersection of a couple of these perpendicular bisectors, right? So with K, I would have had to use these triangles here and these two triangles and these two triangles, like this one and this one. With J, I use this triangle and this triangle. So, but I can use similar steps to show that the point K would be the center of a circle, including the points A, B, and C. So, step 8. I'll be precise with, try to be precise with my language. So steps similar to, let's see, 2 through 7, right? So these steps here. Steps similar to 2 through 7 can be used to show that K is also the center of a circle that includes A, B, and C. Also the center of a circle including A, B, and C, the three vertices. Okay, so it would use all these same justifications and would use similar steps, except it would be this triangle here and this triangle, yeah, it would be this triangle here, K, B, C, and the triangle K, A, C. So those steps would show that K is actually the center. So which is it? Is J the center or is K the center? Well, the fact is a triangle can't have two different centers, right? So it turns out that J and K are actually the same point. And that will be sufficient to to cause us to reject the RAA hypothesis right here. So we assume that the three perpendicular bisectors do not meet at a common point, but meet at different points. Well, if they meet at two different points, that means that the circle containing A, B, and C has two different centers. And you know, I don't think that a circle can have two different centers. The definition is that a circle is the set of all points equidistant from a center, and it will be one unique center. So step 9 is as follows. So step 9. This is a contradiction. We assume that there were two different intersection points, J and K, at least two. There would actually be a third one here, but even with two is enough to reject this hypothesis, because this will lead to a contradiction, because a circle cannot have two centers. Therefore, There's 3 dots mean therefore. Therefore, all 3 perpendicular bisectors meet at the common point J in my diagram. So because all 3 perpendicular bisectors meet at the common point J, that right there is my goal. My goal is to prove all 3 perpendicular bisectors meet at a common point. Here we go to the bottom. We see that we've proven it. All 3 perpendicular bisectors meet at the common point J. And so I'll go ahead and write that QED, signifying that I'm done with the proof. Okay, so that took a little work. I know the logic can get a little bit complicated. These proofs are sort of like when you're first learning proofs, these proofs are typically a little bit more difficult to understand. So if this is confusing, I would recommend also looking at other examples of proofs by contradiction. You can find them on the internet, on YouTube, etc. Okay, so that's the end of this video on the circumcenter. In the next video, we'll be looking at the construction of the incenter. I won't actually be doing the proofs for any of the other triangle centers. For the rest of the time, it's just showing the constructions.